exercises. So the GitHub repo for this is now public, and so the address is https://github.com. My username is Sarah Romanis, and it is Rladies ML2. Or if you go to my repo, my name, Sarah Romanis, is up there as well. And there you can actually just download the whole thing, and then if you make sure it's unzipped, you actually extract from the zip file, or else things probably won't work. The whole folder structure will be there, and there's exercise templates here, and there's also fully worked solutions as well. So if you ever worry that you might be falling behind, there are solutions there. We also have people walking around as well who might be able to help you with your questions as well. So let me know if you have any issues accessing that. There'll be a few packages you might need to compile the slides and also use.
There is Wi-Fi, yes.
Yeah, Wi-Fi.
Wi-Fi is orange, so join the orange network, and then it'll just ask you to give it an email address as a guest, and it should work.
So I thought while you're all getting the repo, I thought I might just start, and you can do that in the background. So today, this is the second part of the machine learning workshop. This one is, as I said, more hands-on. And so last week we covered supervised learning techniques, and if you weren't there for that, it's not you don't really need to be an expert in what I talked about. We do implement some of the methods that we learned about last week here, but it's not too hard. If you look at the argument documentation as well, if you ask people around to just work out what the code is to do those methods. But if you want to ever catch up, there's a link to the slides I showed last week as well, and the repo is also public for that as well. And so a quick recap from last week is, the first thing we start off with was, what is machine learning? And so machine learning is, as I said, the biggest buzzword of all time, right behind artificial intelligence. Someone today, I have an office job, and I went in, and they said, "Oh, what are you doing tonight?" I said, "I'm giving a talk on machine learning." Like, "Oh my God, robots!" I'm like, no. Machine learning is just a way we make statistics sound a bit more fun. All it is concerned with finding functions that take in some data input and are able to predict an output. And mathematically, machine learning problems are simply just optimization problems, which we use R to help us solve. So we don't have to worry about writing down all the algorithms ourselves. And so last week I introduced a few supervised learning techniques. I introduced linear regression, I introduced generalized linear models, random forests, decision trees, and k-nearest neighbors. But I didn't actually tell you how to figure out if your model was any good or not. And so today we're going to have a look at some ways we can assess the performance of our model. And to do this, we first need to figure out what are some metrics first to actually get a quantitative assessment of what we're doing. So we're going to revisit the data set I used for the regression example. And so this data set is a simulated data set. So here we have years of education versus how much money people made in their income. So of course it's simulated because it's very continuous, this education variable. This can be found in my GitHub repo as well. And so what we want to know is if I fit some sort of regression model to this data, how well do I know how it fits the data? And so last week we considered fitting a linear model to this data. So a linear model is just trying to fit a straight line to the relationship. And it resulted in the following line here, so the blue line. And if you want to recall how we actually fit that in R, you can follow the link to the slides here where we use the LM function in R. However, there are many different types of curves you can fit to data sets like this. So, it's not really showing that well on the projector, but here we have a linear line, we could have a quadratic line, we have a logarithmic line, exponential, low s, linear no slope, logistic, and then there's so many other models we could have. So how do we know that, why did I pick the linear relationship as the one to describe this data set? So consider now, I'm going to fit a polynomial curve. So a polynomial mathematically is just, you can write a function. So a linear relationship is y equals mx plus b, where you have x to the power of 1. Then a polynomial has many powers of x. So you could have, this one is up to degree 17, so it might have different coefficients of y equals mx plus m1 x squared all the way up to x to 17 to give this nice looking fitting graph. It's very disgusting. And so what we're going to ask ourselves is, does it fit better than our straight line? So should I have used a more close fitting line function to describe my data? So how are we going to assess the fit? So one way we can assess the fit is the root mean squared error, which is a metric of how far away our fitted line lies away from the observations on average. So what you do is, here is your actual data point. Here is a data point you fit using the line you chose. You then take the difference and you square it. You then sum up these differences and then take the average and take the square root. It's very, the names relates to the formula. So if you say it in the right way, root means squared error, you'll usually write down the right formula. And so there's no, as far as I'm aware, I haven't actually seen a very quick way of doing this. But what you do to find the RMSE in R, if you want to do it as if you were writing down on paper, first you would fit your model for the linear model. So this is the formula we looked at last week. So LM stands for linear model. We're going to pass in our data set, and we're going to tell it we're regressing the response against the predictor. So in this case, the response is income, and the predictors were, the only one predictor was education. So can I predict income from education? I'm also going to fit in a polynomial model. And so I didn't actually show you this one last week, but we're going to learn the code for that today. It's not too important how to actually know how to code it up. But here you also call it a linear model as well. And here you're just saying, we're saying income, we're going to regress it against a polynomial education up to degree 17. Why 17? When I fiddled around with the graph, that's the one that looked the best. So there's no special reason why it's 17. We then find how the predicted values for our line. So the fitted values for the linear model, we use the predict function like we used last week. We pass it our model. We're going to pass it the data frame of our observations. And we're going to do the same thing for the polynomial model. So the only difference between these two lines is that we pass in the polynomial model for the model we're interested in. So to find the root mean squared error, first you subtract your fitted values from your actual values, then you square it, take the mean, and then take the square root. So it's just literally me writing out the formula in R. And so this means that pretty much on average that the fitted data points lie 5 units away from what is actually there. Then the root mean squared error for the polynomial model, you repeat the same formula, but you just put in the fitted polynomial values this time instead, and on average they lie around 2.8 units away from the observed values. And so you might have intuitively guessed that the polynomial model, because that was a lot more tight-fitting to the graph, that would fit better. And the RMSE also corresponds to this. So here we got a lower root mean squared error than the linear model. So you might be thinking, this has a lower root mean squared error. Should I just use this fit instead? So one really big important concept in statistics and machine learning are the concepts of bias and variance. And so in order to minimize test error on new data points, so suppose I've got a new data point, so I've got some more data about income education. I want to minimize the error on the error if I would predict that. Statistical theory, which is outside the scope of this workshop, tells us that we need to select a function or a machine learning method that achieves low variance and low bias. So what are these two concepts of variance and bias? So variance refers to the amount by which our predictions would change if we estimated using a different training set. So the more flexible your model, the higher the variance. So for example, for the polynomial model, where that line really fit closely to our data, any changes or perturbations to that data set, we're going to get a completely different looking polynomial curve as well. Then on the other hand, bias refers to the error that's introduced by just the pure fact that we're approximating when we do statistics. So if I observe data between education and income, any model I fit is just an approximation of what happens in the real world. And the more simple your model, the higher the bias, because you're making a more simple approximation to the real world data. And so more simple models have higher bias, but more flexible models, like the polynomial curve, have higher variance. And so high variance, or we might hear them as quite a lot as overfitted models, can be problematic because if your model is trained very closely to the data and you add a slight little perturbation to it, which might make it change quite a bit, it won't perform as well on your data set. So this is the example where you've trained your model, you then add some noise to what you observe, and now he thinks it's a pigeon. Okay, so it doesn't, high variance models don't do well when there's a bit of perturbation sometimes to the data set. So they only really predict well when the new data point really matches quite closely to what it was trained on. However, of course, we don't want models that are too simple. So high bias or unfitted models also constrain the flexibility of your model as well. So here, don't fit linear models, for example, to something that's clearly not linear. And so as you might have guessed, there is a trade-off between increasing variance and decreasing bias, and vice versa. So as you increase the flexibility of your model, increase the variance, you get a decrease in your bias, but that comes at the cost of increasing variance. So if you want to decrease bias, you're going to increase variance, and so on. And so what we're trying to do is we're trying to find a nice function that, you're never going to get anything quite perfect in statistics, so you want something that's got a good ratio of bias and variance. And so the middle ground for this particular data set might be something called a low-S model. And so don't have to worry about exactly what the low-S does. If you look at non-parametric regression online, there's a lot of information about there. But all this does is it fits a line non-parametrically that you can think of it as a smoothing function, where it just smooths along the data points. So it's called low-S. And it's a nice middle ground between, in my opinion, between bias and variance. So the polynomial curve was a bit too extreme. It was fitting that quite closely. The linear model, even though it looked good at the beginning, we can see here, especially towards the end, we're not capturing that relationship of some curvature around there. And also at the end, that could be a bit problematic here as well. And so the low S is a nice middle ground. If we look at the root mean squared error of the low S as well, so if we repeat the same steps we did with the polynomial and the regression line, we also get our root mean squared error that's in between. So it's not as low as a polynomial fit, it's not as high as the linear model fit, it's right in the middle.
Can I ask a question?
Yeah.
What is the measure of being low or high, or how do you decide, okay, this sounds low and I should increase, or I should use a model that increases the RMSE, or 5 point something was very high, then I should go lower?
There's no set hard or fast rule. It's just the RMSE is usually used a lot comparatively between models. So you can't actually, a lot of time, using the RMSE by itself is not enough to look at something. Of course, if you had a model that was way off the mark, you could really higher RMSE like 100 or something, then you're doing quite poorly. It will make a lot more sense in the context of when we look at cross-validation. So I'll explain then when it's a lot more useful. But it's just a metric we can use to assess how close our line is to the data at the moment. But in this case, the RMSE wouldn't actually help you decide between these three models. It just shows you that it's a metric that we use, but a lot more, it's more of statistical intuition in this case. So the RMSE is a metric used for regressions when we're predicting a numerical response. In the classification setting, we're looking at the case where we're predicting against classes. So the RMSE doesn't really work in this case because your data is either, for example, in this case, it's 0 or 1, and the RMSE would give you a value that's not between 0 and 1. So you can't really use this to assess how well a classifier is working. So in this case, we're going to have a different metric for looking at how well a model performs. So again, we're looking at a data set we used last week, which was the exam data set. So 2 exam scores are given for each student, and label represents whether or not they pass or fail the course. So here we're just having a look at first couple rows of my data set. Here the student failed the first exam, passed the first exam, but of course wasn't good enough and they failed the whole course. And so if I build a classifier to use this information about the exam scores, how do I know how well it is predicting pass or failure rates? And here's just a plot we can have a look at, which is the exam scores against each other, and the colouring just shows whether they pass or fail. And so one metric we can use is called the resubstitution error rate. It's a bit of a mouthful, as well as the RMSE. It's a measure of the proportion of data that we predict correctly when we try to predict all the data points again using the fit we found from our model. So here, what you do is, for each data point, you fit your model, for example, you then refit all the data points, and you count how many of them you got wrong, pretty much. And as a proportion of everything else. So if your classifier does really well, that will be 0, because you got none of them wrong, and if you got them all wrong, that will be 100%. So last week we used a general linear model to fit this data set. And so we're going to fit a GLM against all the predictors like we did last week. So the notation for this was, we're going to call a GLM. The data set we're referring to was called data. We're going to regress the label, so the pass or fail, against all the predictors. So the tilde dot tells us, don't have to worry about writing exam 1 plus exam 2. You can just easily make the shortcut and tell it use everything. And this component here was we're using a binomial family because we've got a binary response, and the link is the logistic link. So in my part 1 slides, we had talk about the different links we can use to transform our continuous outcome to a 0-1 space. Again, to find the fitted values, it's very similar to what you do in the linear model case. So we're going to use the predict function. We put in our GLM that we found we fitted. The new data is the data set we used before, so it's going to be subsetting on the predictors, we don't want to put the response in there as well. And we're going to tell R to predict out a response. So the response in this case is a probability that my class equals 1, or in this case a probability that we passed. And then, so that's the probability of being class 1, and if you want to round it up to the actual class, you just do round. And so probabilities that got above 0.5 would get rounded up to 1, and if your probability was less than 0.5, you get rounded down to 0. So we get a 0-1 output from this as well. And so the error is simply the mean of how many, if I do fitted vowels does not equal the true vowels, I get a true or false vector. And if you take the mean of that, you just get the percentage of how many of them were true. Oh no, how many of them were false, my bad, false. And so in this case, the resubstitution error rate was 11%. So 11% of my observations weren't fitted correctly. So that's one metric we can use for this model, the resubstitution error rate. Another thing we can consider, which was brought up last week in the random forest output, is the confusion matrix. And this comes from the carrot package, which we'll use at the very end of the workshop to do cross-validation, but it's also very useful to get metrics for classification performance. And so the confusion matrix just tells you in how the algorithm was underperforming. So was it, which class was it getting confused on the most? So here we have the same code as last time, so we still got my model fit. I've still got the fitted values. Here I call the library carrot, because where the function comes from. And the code we're interested in is called confusion matrix, aptly named. And what you do is you put in two vectors. You put in what you predicted the values to be, and you put in a vector of what the true values were. Then it goes ahead and creates a table of how well, or how the data set got confused. So I'm going to call confusion matrix. I'm going to just call the object confusion.dlm. There are quite a few things that come out from that confusion matrix command. So we don't want to. All of it's important, but to focus on, we only want the table output. So I'm going to just extract the confusion table itself. And here I get the confusion matrix. So what you do is you read the table vertically. And so for the prediction is what you predicted, the reference is the true data. And so for what the values that were truly 0, you got 34 of them correct, and you guessed 6 of them as actually 1s. For the references, the values that were actually 1, you predicted 5 of them as a 0 instead, and 55 of them as a 1 correctly. So you can see which ways it was getting confused. So here is pretty balanced in how it was pretty symmetrically misconfusing the 0s and 1s. But sometimes you can have a big imbalance between what it thinks is a 0 and a 1. And so for an algorithm that's doing really, really well, you want to have higher values on the on-diagonal elements. That means your reference and your prediction match up. And then for algorithms that are doing really well as well, you have lower values on the off-diagonal, so you're not mismatching. So yeah, so out of the 40 failures in my data set, GLM successfully predicts 34, and out of the 60 passes in my data set, GLM successfully predicts 55. So the confusion matrix just helps you see how it got it wrong. So the error rate is one quick metric to see how well it was going. If you want to go dig deeper into which way it was getting confused, the confusion matrix also helps you do that. So here is the workshop component. So on the GitHub repo, there is a data set called diabetes, which is one of the most overabused data sets in statistics. I used it in my third year course. So what it is, it's a data set that contains 768 observations and 9 variables, and it's to do with predicting whether a patient has diabetes or not, given some measurements from the hospital. So you've got if they've been pregnant, glucose, blood pressure, thickness of the skin, insulin, BMI, pedigree, age, and if you go on the GitHub repo, a lot of these things are explained, what they actually mean as well. And so your task is to build a machine learning model to predict whether or not the patients in a data set have diabetes. And so you can use whatever model you liked from last week. If you liked k-nearest neighbors, you can do that. Like GLM, you can use that, like random forests, or decision trees. It's up to you which model you liked the most. And then the new component is to assess the performance of your model using the resubstitution error rate, and then look at the confusion matrix as well. And so I do have, there is a template, so you can start filling in the template. Is the model metrics template. And there are solutions for GLM, random forest, rpart, and k-nearest neighbors as well. So if you ever get confused on like maybe some different syntax, you can have a quick peek at the solutions and have a look. And so, yeah, that's the task. So hopefully, if you have any issues downloading the repo, let me know, and I can come around to help if you've got any issues. And then we'll move on to cross-validation next.